Hello, everyone, and welcome. Today, I am excited to present our work on AI-driven biomedical innovation. We will explore how high-performance computing enables federated learning to build robust, cross-site pathology AI models, specifically focusing on non-muscle invasive bladder cancer. Our infrastructure enables cross-hospital pathology AI without sharing patient data. By utilizing NVIDIA Flare, we connect KMUH in Taiwan and VUS-HKL in Lithuania. Raw whole slide images remain secure locally on heterogeneous GPU setups, while only model weights are aggregated globally to predict staging, grading, and recurrence risk. Traditional staging and grading guide bladder cancer treatments, yet clinical outcomes remain highly heterogeneous, with over 30% of BCG-treated patients experiencing recurrence. Our computational pipeline aims to bridge this clinical gap by translating tissue morphology into actionable risk stratification while strictly maintaining data boundaries. To capture clinical utility, we define three computational targets: staging, grading, and BCG recurrence risk. Using a Dino V2 feature extractor, our model learns joint morphological representations from the same tissue patches, directly linking diagnostic features to prognostic outcomes. Hospital networks face massive domain shifts from different scanners, staining, and resolutions, making single-site models highly fragile when deployed elsewhere. By comparing VUS-HKL and KMUH datasets, we show that federated learning is essential to overcome these shifts and achieve reliable, generalizable performance across diverse clinical environments. Our goal is to run digital pathology AI in real-world clinical environments. This framework combines secure distributed training, cross-scanner robustness, and attention-guided explainable embeddings. By operating across heterogeneous GPU networks rather than single machine simulations, we address the actual deployment challenges that clinical systems face daily. Under our NVIDIA Flare framework, KMUH trains local models independently on their respective hardware. Only the neural network weights are shared and aggregated using the FedAV algorithm over a secure IP whitelist. Patient data and whole slide images never leave their home institutions. Our computational pipeline starts with tile extraction and magnification normalization. Next, Dino V2 extracts patch features, which feed into a CLAM architecture for staging and grading. Finally, we fuse these embeddings and apply a Bayesian-Gaussian mixture model to cluster patients into low and high-risk recurrence groups. This study evaluates over 1,400 retrospective cases across highly heterogeneous cohorts. VUS-HKL provides over 1,000 cases using Leica scanners, while KMUH utilizes Hamamatsu scanners powered by NCHC's Taiwanese computing platform. This diversity ensures our validation captures true real-world variability. The results are compelling. Federated learning achieved 86.2% in staging and 79.2% in grading. Most importantly, it dramatically reduced the cross-site performance gap, outperforming single-site models by up to 13% on external validation without any central data pooling. Beyond standard diagnosis, our computationally derived fusion factor successfully stratified recurrence-free survival. In both cohorts, the high-risk and low-risk groups showed statistically significant separation, with hazard ratios exceeding 2.7, proving that AI-derived morphology contained critical prognostic signals missed by traditional staging. Successful clinical translation requires both biological validation and mature infrastructure. While our model captures rich morphological features beyond standard labels, we must continue testing across more scanner brands and clinical settings. Moving forward, we aim to scale this federated framework to larger hospital networks. Ultimately, clinical AI is both a computational and a coordination challenge. We have demonstrated that federated training improves cross-site robustness and that combined staging and grading features hold key prognostic value. Our vision is to scale this secure, multi-institutional pathology network to support global clinical decision-making. Thank you for your interest in our research. At the National Center for High Performance Computing, we remain committed to empowering the future of medicine through scalable, secure, and collaborative AI innovation.